Okie dokie. Welcome to Working Through Math 1026 Lab 5 with me, your lab partner. So today we're going over a lab that's dealing with like approximating areas under curves using the left, right, midpoint, and trapezoidal sums. And then we are going to use those methods to apply them to some real world like lake example or waterway example. So, to summarize the first bit here, they're just talking about left, right, midpoint, Riemann sums, the rectangular sums, and then the trapezoidal sums. We have all these objectives here. Most of them you should be able to do already because you've already had an exam on them. Looking at visualizing the approximation techniques. They basically introduce us to, let's start with this. They introduce us to this situation, this chromatography situation. They say below some function b of x equals x times e to the negative 1.7 x squared on this interval 0 to 2. The area of the shaded region represents the total amount of pigment in a chromatography band. All right, all you have to know is that we're going to use this function, x e to the negative 1.7 x squared. Later, you will learn that you can actually find the exact area under this curve using fundamental theorem of calculus, substitution method. Okay. You don't need to worry about that. You just need to know that the actual exact area under this curve, the function we are dealing with, is 0.293790007. Mark this number. We will use it later. All right. So, partitioning the interval. So here they're just talking about how to break up an interval, say from 0 to 2, into 4 equal subintervals. We do 2 minus 0 and divide it by 4. You should already know this. This is from, previous quiz or exam. Okay, so like for this one, the value of delta x would be just 0.5 because we go from 0 to 2, a gap of 2, and we cut it into 4 equal segments. So each subinterval, each segment is 0.5 in width. And then you need 5 values to partition an interval into 4 equal pieces. So if we're going from 0 to 2, 4 equal segments, we're going 0.51, 1.52. Sketching the geometric figures. All right, I've pulled up my iPad just for this. They want us to practice just sketching the rectangles and or trapezoids onto these curves here. So I'll demonstrate that just so you can get an image. All right, so for the left sum, keep in mind we're going from 0 to 0.5 to 1 to 1.5 to 2. We're breaking the rectangles up like this. For a left sum, you'll put dots starting with the leftmost x value. So starting with 0, you're putting a dot on the curve, dot on the curve, dot on the curve, dot on the curve. You're going to put dots on all those. You're going to put dots on the curve at all those x values except for the rightmost x value. And then these points will be the heights of your rectangles that you will draw. So the first one's 0, basically. And then the next one from 0.5 to 1 has a height equivalent to the height of the function at 0.5. And then the third rectangle has a height equivalent to the height of the function at x equals 1. And then the last one, the height comes from x equals 1.5. So you'll notice the left corner of each of these rectangles, the first one's not really a rectangle, that's why I did that. The left corners are touching the curve. All right. So now, doing the right sums, we're going to put points on the curve for all these x values except the leftmost x value. So the height of each rectangle is coming from the right, what they call the right endpoint of each of these like smaller intervals. So hopefully that makes sense. It's a little rough, but you see the right corners of each of these rectangles are touching the curve as we go through. Okay, so then midpoint sum. Okay, so we're still going, the rectangles will still exist from 0 to 0.5, from 0.5 to 1, 1 to 1.5, and 1.5 to 2. Except the height of each rectangle will not come. So like the first rectangle goes from 0 to 0.5. The height of the first rectangle will not come from 0 or 0.5. It'll come from the y value that is corresponding to 0.25, the middle of that rectangle. So at 0.25, we put a point on the curve. You know, for the x value, 0.25. And then for the x value of 0.75, between 0.5 and 1, we put a dot, 1.25 and 1.75. And so then we form rectangles still spanning from 0 to 0.5, 0.5 to 1, and 1 to 1.5, and 1.5 to 2. Just passing through those points. So the middle point x value gives us a y value that gives us the height of each of those rectangles. All right. So now trapezoidal sums, we're still going from 0 to 0.5 to 1, 1.5 to 2, except we can put dots on the function at every single x value. And what we're going to do is connect each pair of dots with a straight line. That's about as straight as I can get it. And then like a straight line down here, if I can draw that. So it may not look like it, but that's our first trapezoid. Second one's definitely going to look a little bit more like a trapezoid. We connect the dots with a straight-ish line. That's our second trapezoid. Then we connect the dots with a straight line. That's our third. And then fourth. So the biggest distinction with the trapezoidal image is that, you know, obviously we're not using rectangles. You can actually use a slant for the top edge between the 2 points each time. All right. That's the image stuff. I don't think I'm using the iPad anymore. So let's get that out of here. All right, let's get back to it. So basically using Excel, they tell you to open up this Excel document. Go ahead and label, you know, all these tabs down here: left sum, right sum, midpoint sum, trapezoidal sum. And for the first 3 pages, you'll have like x, bx, left sum error, same thing, just with right sum error, midpoint sum error, and we'll talk about the extra stuff once we get to the trapezoidal part here. All right, so I'm trying to find a good place to put my dang cute face here. All right, so they tell us basically to just use these x values we've already talked about and the function they've already talked about. So they have like 2-3 pages dedicated to just doing something that you should already know how to do. So we're going to put our x values from 0 to 2, going 0.5 in between each time. So they tell you to not just type in the x values, but I'm going to type in these first 2, highlight them, and then drag down until we see 2. So we're going from 0 to 2, and then we're inputting the function. What they'll tell you for the left sum and the right sum in the midpoint sum is that you only need 4 x values. So this is just one way of going about it. Technically, you do only use 4 x values for the left, right, and midpoint sum. The way I might have taught you, if you learned from me, or the way you might have learned a left sum or a right sum, is just to go ahead and put all the x values and then just use the leftmost values and leave off the right one. Or if you're doing a right sum, to use the rightmost x values and leave off the leftmost value, right? So what they might actually have you do is, for a left sum, if we're going from 0 to 2, we don't actually use that 2. Okay, so you might see them say just like fill out the x values from A2 to A5. That's why. So you're only using these 4. All right, so we're inputting this function. Let's see if I can find it. Here it is. So x times e to the negative 1.7 x squared. So we do x, we click on A2 times exp to the negative 1.7. So we just type negative 1.7 times x squared. So we click x, we square it, close parentheses. That's it. Hit enter. We can drag these down to fill in the other b values. And so for a left sum, the nice thing about, I guess, just using these x values is that you like don't have to think about leaving off any of the b values. You can literally just do the formula. We do the width, right, 0.5 times the sum of all the y values, or the b values in this case. So 0.5 is our width times the sum of the heights gives us the left sum here, 0.27115. And I think they want a few more decimals, so I'm going to do that. And then the left sum error comes from, they say the error in your approximation is simply the absolute value of the difference between the left sum and the exact area. So enter the absolute value of C2 minus the exact area in cell D2 and round to 8 decimal places. So the exact area, again, going back to the start here, this was the exact area, that thing they got from the exact like integral, the area under that curve, right? So we're going to use that. One thing I don't like about this is later on they ask what the error was, and then they ask whether it was an over or under estimate. Now, if we're taking the absolute value, I might try to explain this in a moment once we actually calculate it. So let me calculate it how they actually had you do it, and then I'll explain my frustration. So ABS, C2 minus exact area. C2 minus exact area, which was up here, 0.29379. 29379,007. Close that off, hit enter, and we get this error. We get the error that they were talking about, right? So in this little table here, they eventually want you to write out the error and the overestimate, or when, okay, so all this stuff basically that's going to eventually be in Excel. My frustration with this is this: when you find the absolute value, you always get a positive value, right? From that value, we can't tell whether it's an over or under estimate right away, or I think it's easier to tell whether it's an over or under estimate if we don't take the absolute value. Because if you were to just do the like exact value minus the approximation, let me make sure I have this right. No, if we do the approximation, this left sum, minus the exact value, so if we take out the absolute value, you can see me trying to do it at the top here, delete that, and then delete that, and we hit enter. See how we get this negative value? That negative is a sign for an underestimate, because the approximated sum value was not as much. It was not as high as the exact value, which was 0.29 something. So if we got 0.27 something, that's an under approximation from 0.29, right? So naturally, if you just do C2 minus that, you get this negative value, and the negative tells you it's an under approximation. If it had been positive, it would have been an over approximation. All right, so that's my getting some off my chest there. There we go. All right, so all we're doing is this same exact thing for the right, midpoint, and we'll talk about trapezoidal. So now for the x values, again, we'll go from 0 to 0.5 to 2. And then for the right sum, I would always have instructed you to just use the rightmost x values, leaving off the first x value. So what I'll do is delete the 0, and I'll move these up here. So the x values they would want you to use in this case is just 0.5 to 2. We'll input the same exact function. So I'm going to see if I can just copy this. We'll see how this goes. Oh, I have no idea what just happened. Something did not go right. We're going to copy that again. We're going to go here. I don't know what's happening up there. It's just messing everything up. All right. Forget I tried that. Just get me out of this. All right, I'm sorry. Give me 2 seconds. What the fuck? All right. 1.5. What is this thing doing? 2. All right. Did this get messed up? It did get messed up, and I can't fix it. No, it's still 0. It was 0. Okay. All right. Let's just type it in again. Sorry, this is very unorganized. I thought this part would take like 2 seconds. Now it's taking a month. So we have x times exp raised to the negative 1.7 times x squared. Hit enter. We drag this down, get all our b values again, and then for the right sum, the width is still 0.5. So we multiply that by the sum of the heights, the b values, right? Hit enter. We get also about 0.27. 222, and you'll notice it is very similar to the other one because the value for 0 and the value for 2, we're not very far off. They're both about 0. Anyway, so I'm going to do it my way with the error. You can do it their way. Just being a rebel about this. So I'm just going to do that minus the exact value. 0.29379007. We hit enter. We can see that it's negative. That's still our error. It's like that much different from the exact value, and it's negative, therefore it is an under approximation. So like if you were hypothetically filling out this table, you would say under for left, under for right, and now we're on to midpoint. All right. So the midpoint, let me type out our original values first, and then we'll talk about midpoint. So remember from our graphs, I should have kept my iPad up. Oh well. On the graphs where I drew the midpoint situation, we said that our first rectangle was still spanning from 0 to 0.5, right? But we didn't use 0 and we didn't use 0.5 to find the height of that first rectangle. We used halfway between those two, right? So we can tell pretty easily that halfway between these two x values is 0.25. So basically 0.25 will just be our first x value. And then because our width is still 0.5, we still want to go up by 0.5. We don't want to go up by 0.25 each time. We want to go up by 0.5. And so if we highlight these two and just drag it down, we get the x values that are in the middle of each subinterval from 0 to 2, and they will create the heights that we need for the midpoint sum. Okay, so I'm going to try inputting this function again. X times exp times negative 1.7 times x squared. All right, click and drag this down. Midpoint sum, again, we're doing the same thing, 0.5 times the sum of these heights. Hit enter, we get about 0.305. Okay, we can tell that is already a little bit bigger than the exact value, right? So if we do this minus the 0.29 yada yada, 0.293790007. All right. So we get this error that is about 0.0114. Because it's positive, naturally that is an over approximation because the approximated value was greater than the exact value. So that's an over approximation. So on the table, you'd plug in an over approximate, or you'd write over estimate, over approximation for the midpoint there. All right, let's talk trapezoidal sum. They have you do kind of the same thing. We'll start with our x values. In this case, we can use all 5 values. They have a little section about this in the trapezoidal method. I know I'm kind of ignoring, everything I've highlighted here, but there's really no need to go over it. So B, we're inputting our function still, so no change so far. So we're doing x times exp raised to the power of negative 1.7 times a squared, right? A2 squared, x squared. All right, checks out. Drag those down, get all these values. They look weird because I've tightened up the column here, but if we spread it out, we can see they go to a lot of decimal places. Now, coefficients and products, kind of an extra dumb step. You've already learned how to do a trapezoidal sum without doing these coefficients and products, hopefully. I don't know what I just clicked on. What did I just do? I don't know. Anyway, coefficients, they're talking about this trapezoidal method right here, where within the heights that you're adding together, you see how they start with like 1 times the first y value, 2 times all the in-between y values, which we've talked about before, right? 2 times all the middle ones, and then 1 times the last one. So they're talking about the 1s and 2s as the coefficients. So because there aren't many y values, we can manually type in the coefficients that they're talking about. Generally, you would not do this. This is a waste of time. Coefficients, first, 1 times the first one, 2 times all the in-betweens, and then 1 times the last one. So then the products, they're literally just talking about like this times the coefficient. So B2 times C2, and you drag this down. So what that's doing is like automatically multiplying the heights by the coefficient, so by the 1s or by the 2s, however you need it, right? So then as a result, we can more easily calculate this, but you have to put in this work to, you know, do that crap. So anyway, trapezoidal sum, we always do 1/2 in front times the width. So that's why they do delta x divided by 2. So the divided by 2 is the 1/2 times the width, which is 0.5, times the sum of these products. And so this saves you from having to do like the first one plus 2 times the sum of the middle ones plus 1 times the last one, because we've already kind of done that work. Okay, we just do that, hit enter, we get our trapezoidal sum value, and then we do our error the same way. I'm just going to do this minus the 0.2937007. Right about the time I've done this last one, I've finally memorized that 8-digit thing. All right, is that 8 digits? I feel like I'm missing something. I did miss something. I just fucking, all right. Did I miss that in the others? No, just that last one where I said I memorized it, and I had not memorized it. Got humbled real quick. All right, so we have a negative value there. That's an under approximation. So you should have everything to fill in this little chart here. So I think we had like, what was it? It was like under, over, under. And then so ordered 1 to 4, best to worst. So the best approximation would be the one with the least amount of error. The worst would be the one with the most error. So I'm not going to determine that. I might determine like maybe the best and the worst. How about that? So 0.022, 0.0220, 0.011. Oh. Okay. 0.011. This midpoint sum, that's probably the best. So that's number 1. And then the worst error. Am I tripping? Hold up. That was 0.021 the whole time. Okay. Oh, my head hurts. Okay, what are we doing? I think the left sum's the worst one. It's 0.0226 away, and I think that's more than all the others. Okay, so I'll leave you with that. You can figure out the rest. Which of the methods gave you the best? Okay. Let's go into the application. We've been going for 22 minutes. All right, let's pick up the pace here. I'm going to close out of this, get a little better look at this. So they're talking about some lake water. They want to control how much water is gained or lost. We're dealing with inflow and outflow rates. You want to determine if Lake Mead had a net gain or loss of water during the years 2014, 2015, 2016. Net change is equal to total inflow minus total outflow, which makes sense. The amount of water in a lake is going to be based on the number, like the amount of water that's flowed in minus the water that's flown out. That's going to be like your change over some period of time. And so here they represent it with like integrals of inflows, because if you're integrating an inflow, what you get is an amount of water that has flown in, right? Flown in sounds like it's flying in, but flowed in maybe. So, and then the same idea, you subtract the outflow integral. So finding the integral of the outflow gives you an amount of water that has flowed out. Okay, so inflow minus outflow integrals. Water flows in from a couple of different places. The dam upstream, they have it like right here in this image. I really like this visual here. So they have water flowing in from the dam and just like other sources, other minor streams. But then they say some of the water is lost due to evaporation, Southern Nevada Water Project, SNWP, and then the Hoover Dam. Most goes out to the Hoover Dam. Okay, so this is the inflow up top. This is the outflow. Okay, what do we got here? You're going to integrate the inflows and outflows. You can't calculate the error because you don't know the correct answer. Okay. We download this document, column G. Don't need to worry about that. Okay. All data points are in 1,000 acre feet. Whoops. there we go. All data points are in 1,000 acre feet. So where we see like 601, that represents 601,000 acre feet. What does acre feet mean? Acres are describing the area of the surface of the water. The surface area is measured in acres. You can think of like, I don't know, usually when you think acres, you think land, right? You think like the square footage of land, but it's like, it's not square footage, it's the acres. So we have acres, and then we have feet. So we have acres on the surface, and then feet is describing the depth, the height of the water. What do you call it? Surface elevation. Yeah, that's what they're calling it. Okay. All right. So 1,000 acre feet. Left sums. Okay, so they want us to use left sums, calculate the integral. So I don't know if I got like a magic document or something. I think they gave you all these values. So what they're giving you here are all the left sum values for the Glen Canyon release, side inflow, evaporation, SNWP, total release. I think, like for all these here. We can check that. Yeah, so like left sum for this, left sum for this, we leave off the rightmost value, that's 64, right? And then they're doing the same thing each time. Yeah, okay. So they might just give you all these values, but then you just have to know how to use them, right? So let me just see if I'm missing anything else. Add together the inflows and the outflows to calculate the total inflow and outflow. Use these to calculate the net flow and write the units. Finally, assuming the surface elevation of approximately 1,100 was like the beginning surface elevation and a beginning surface area of approximately 88,700 acres. Given your calculated net flow, estimate how much the elevation of the lake has changed over the 3 years. Determine your estimate for its new surface elevation. Okay, let's give this a go. So again, they give us all the basically these are all approximations for the amount of water that has flowed in, and then this is all the flowed out. So release yeah, okay. I don't know if there's like there's supposed to be a specific spot for, maybe I missed something about, we'll just put it here, total in, let's say total out, and then net. Okay, so the total in is just going to come from the sum of the in values. So we'll just that plus that. Okay, and then total out is just going to be, I'll just do sum of those three. So the total out is all these evaporation, this project thing, and then the release into the ocean. So the total in and the total out. So to find the net, again, we do total in minus total out. So we'll do this in minus this out. We hit enter, and the net water change based on left sums is negative 2750, meaning they lost approximately, that's in what, 1,000 acre feet. Oh god, it's like 2 million. Basically, you know, this value times 1,000. Well, now I can't see it. Hold up. Put it down here. Bam, times 1,000. Okay, yeah, so that's they lost 2,750,000 acre feet of water. So it's a volume of water. They lost that much. Okay, let's just do the same thing for the others. All right, so this is the right sum. Again, they calculate all the right sums for you. Don't know if that was intentional or not. I think they might have said it in part of the lab. Might have brushed over it. So I'll just say total in, total out, and net again. So we'll just get a closer look at these here. So again, we're doing just these two added together. Bam, bam. Equals sum of these three added together. So total in, total out. Do a net, that minus that, hit enter, we get negative 2412. Again, we'll do we'll do this times 1,000. All right, so it lost 2,412,000. Now let's do trapezoid real quick. They've calculated the hard part for us. They did the trapezoidal sum. Did they? Now that doesn't look like a trapezoidal sum. They just like copy. Well, let me make sure these right values are right before I jump right on into it. Yep, those should be good. They didn't do the right trapezoidal thing unless I'm tripping. Who calculated it? Who was in charge of this? That's annoying, right? Okay. Well, I'm going to calculate my own trapezoidal thing because these are not right, I don't think. Let me try this one. They're all just 0.5 times the sums. That's not going to give you a trapezoidal sum. Okay. We're going to calculate our own. We're going to get rid of these. I don't want to get rid of them. Maybe there's a reason they're there, but let's do a trapezoidal sum. We're doing 0.5. We always start with 1/2 times the width, which is just 1, which is why these probably started with 0.5, but then the sums just aren't right. So we do the first y value plus 2 times the sum of the in-betweens plus the last y value, right? We close parentheses, we hit enter, and I think we could drag this down. No way, would that work? I don't think so. I think it would keep using the wrong cells. Okay, we're just gonna keep doing this. So 0.5 is the trapezoidal part, the 1/2 times the width, which is still 1. So I'm just gonna do 0.5 times. We don't need to do the 1. I'll do the first y value over here. We're on to the Glen to Hoover inflow, plus 2 times the sum of all the in-betweens plus the last. Close that, hit enter, we get this. Okay. Man, I mean, they really messed that up. I don't know if y'all's documents have this or not. I hope they do, and I hope y'all are seeing that these are very wrong. And hopefully I'm not like roasting someone's document that they sent me. I'm pretty sure this is like the standard one that they gave you all. So again, same formula. Sorry, I was not more prepared for them to be messing up like this. But again, we're doing just the same formula the whole way down. SNWP. 2 times all the in-betweens plus the last one, close parentheses, hit enter. All right, we just have one more. 0.5 times total release, sum of first total release plus 2 times the sum of all the middles, close that off, plus the last, hit enter. All right, so yeah, I'm confident in myself. These are wrong. We'll do our total in, total out, net, zooming in. All right, so dealing with these guys here, we're doing sum of the first two. This is all the inflow. Total out is the sum of the out, the evaporation and the releases, all those. So then the net is this minus this, in minus out. So then we'll do what we did in the other one. Since these are in 1,000 acre feet, we do this times 1,000 to get a more real representation. Make sure to spread this column out so you can see an exact number. So this is also about negative 2,581,000. Had you used their values that they gave you, you would have gotten this value would have been way smaller, and then this net, it all just would have been wrong. Okay. Whew. So now let me go back to the question they were actually asking. That's very important. So we have all the net flows, right? These are in, this is acre feet, right? and then this one would have been in technically 1,000 acre feet. So you can use either units you want with either number, but this is 1,000 acre feet. This we multiplied by 1,000, or this we multiplied by 1,000 to get this. So this is just acre feet. Okay, I mean we're going on like 35 minutes. Is not too bad. The question they say assume a beginning surface elevation of 1,100 feet above sea level. That's like the height above sea. I think sea level was the phrase I was trying to think of earlier. The height above sea level, and a beginning surface area of approximately 88,700. So given the net flow, estimate how much the elevation has changed, and then determine the estimate for the new elevation. Okay, we got this. So this value is how much the volume has changed in acre feet. They said the surface area was originally 88,700 acres. If we take acre feet and we divide it by acres, the number of acres, we will get the number of feet that it has changed by. I hope. I'm pretty confident in that. And then the number of feet it has changed by, the feet is referring to the height of it, the depth. And so that'll tell us like how much the feet above sea level has changed. Okay, let me do this again. Oh God, don't do that. All right, we're doing 88,700. So acres, so 88,700. All right, so if we divide acre feet by acres, let me get a more zoomed in deal here. That's beautiful. All right, so if we divide this divided by, you can't see it, but it's K12, so K12 we'll type in. If we divide this by this, we get a change of 29 feet. It's decreased 29 feet from the original height. The original feet above sea level was 1,100. Let me double check. 1,100 feet above sea level. Okay, so if it has changed minus 29 feet, we do, good night, K15, I'm mad because I can't click on it, plus the change, not minus the change. It's already a minus, it's already a negative, so we just add K15 plus K13. So the new feet above sea level. All right, so maybe I'll call this old feet. Old feet, yeah. All right. Right. Acre feet, acres, feet. Sorry, I got a bug flying around. The old height above sea level, new height above sea level. So that's the new surface elevation. That's probably what I should have called it. New surface elevation. That's what this is. Surface elevation. Old. I like old feet. I'm going to call it old feet. It's the old surface elevation, old feet. All right. That was for trapezoidal. Now we have to go back and redo that, or not redo anything, but do that for the others. So let's see if I can do it a little bit faster now that we know what we're doing and I don't have to explain as much. So this is acre feet. This is acres. We're going to do feet here. We'll do whatever I did before. We'll call it old surf elevation, new surf elevation. All right. And the acres were still the same. Like we probably could have just copied a lot of stuff and pasted it. Okay, 88,700. So 88,700. We still do this divided by that. So we get about 31 feet change. So it was 1,100. So we do equals N11 plus that, plus the change. So the new surface elevation would be about 1069. Keep in mind these are in feet. I don't know if I need to say that. The height above the sea level is in feet. All right, let's copy this. Put that here. Nice. This is for the right sum. This was in acre feet. The acres was 88,700. Yeah. So we divide them. We do this divided by n7. We get negative 27, so that's how much the feet has changed by. So the old surface elevation was 1100, so the new one should be n10 plus negative 27. So 1072. So we got, for the new surface elevation for each time, we got 1069, 1072, 1070. Beautiful. All right, have we done everything we needed to? Let's see. On the second sheet, blah, blah, blah. Okay. First point, last point. Okay. Total inflow, total outflow, net change, units for these calculations. I've done all these in the situations here in the Excel documents. Let me just pull up and give you an example. Total in, so let's use left sum. So left sum, we have all these values they gave us. The total in, so let me back up. First point, last point, delta t. Delta t is 1 for all of these. First point, last point would be like, I mean, it's different because you'd have to make like a list of the first points. The first point for the left sums are 601, 430, or sorry, 43, 49, 558. But the first value for the right sums would just be the next one, 800, 45, 33, 8, 605. The last points for the left sums would be the second to last one. So you know, for a left sum, you leave off the rightmost value. So you would go up to 750. So 750 would be the last point of the left sum. 750, 77, 42, 16, 751. The last point of a right sum would be 898, 64, 36, 9, 542. You get the idea. For trapezoidal sums, first and last would be, well, they use all of them. So they use 601 all the way down to 898. So you would use first and the actual first and last of every list. Okay. All of these values were the ones they gave you, except for the trapezoidal ones, because they were wrong on those. So we have to use our new trapezoidal ones. All right, let me get back to it. All right. So like these, oh, cheese and rice. All right, these values up here. 25, 651, that's the Grand Canyon. 2216, side inflow. Evaporation losses, 1629. 668, you get the idea. So the units for those calculations those are also 1,000 acre feet. 1,000 acre feet, 1,000 acre feet, 1,000 acre feet. Total inflow, that's what we were calculating here and here. Total in and then out. And then net change, we calculated here. Negative 2750. Those were all in 1,000 acre feet. Change in water level was our negative 31 for the left sum, and oh yeah, change in water level. Oh yeah, sorry, I got mixed up. Negative 31 would go here. Estimated surface area, I guess would be like our new surface area. So like 1069 would be the estimated one, and then units for that calculation would just be feet. So each of our new estimates would go at the bottom here. So like for the right sum, the change in water level is negative 27. The new surface area in 2016 would be, or surface elevation would be 1072, about 1073, and that's in feet. And then you get the idea for the trapezoidal one. I'll go ahead and show you since this video is long anyway. Here we go. Negative 29 is the change. 1071-ish is the new surface elevation. Units is feet. Units are feet. All right. Very in-depth, very hands-on. Sorry, I got distracted. Very hands-on, working through the lab together. If you have any questions, please let me know. Thanks so much for sticking with me. Hopefully I answered any questions you might have had. Shout out to the MPO for messing up the trapezoidal values that they gave you. Yeah. All right. Thanks for watching. Hope you learned something. If you have any questions, let me know. All right. Bye-bye. 44 minutes.